Usually when you stand at the edge of a vast modern farm field and just look out at the horizon, there is this expectation of nature.
Right. You expect to see the natural world.
Exactly. You see the soil, the crops, the open sky, and you just assume you're looking at the earth doing what the earth naturally does. You think you're looking at a landscape shaped by, I don't know, thousands of years of rain, wind, and geological time.
Which is a completely reasonable assumption for you to make.
Right.
That is, until you realize that nature doesn't build in perfectly flat, multi-mile geometric planes.
Yeah, natural terrain rolls.
It rolls, it dips, it has these subtle little contours. When you look at an agricultural field today that is flat to within a fraction of an inch across hundreds of acres, you are not looking at nature. You are looking at a highly engineered mathematical surface.
And the crazy thing is, the only way it got that way was because a massive roaring tractor dragging tons of heavy steel was guided across the dirt by a spinning invisible beam of red light.
That sounds like science fiction.
It really does. And that is the mission of our deep dive today. We are looking at a stack of declassified USDA Agricultural Research Service documents, some original 1970s engineering catalogs, and historical narratives about land leveling.
The source material is just fascinating.
It is, because what they reveal is a completely wild story. American agriculture didn't adopt lasers because it was a cool, futuristic novelty. They did it because of a wild collision of Cold War geopolitics, actual geological collapse, and just this sheer desperation to survive.
Yeah, the 1970s were an era of compounding crises. I mean, we often think of technological advancement as this slow, steady march forward.
Right, like step by step.
Exactly. But in the world of heavy agriculture, the leap from manual surveying to laser-guided robotics happened in a dead sprint.
A total sprint.
The pressure squeezing farmers in that specific decade were so intense that they took theoretical laser physics stuff that was barely out of the laboratory and bolted it directly onto the heavy iron of agricultural tractors.
Well, let's start with the most immediate pressure they faced, which hits right at the wallet, the energy shocks.
Oh, absolutely.
We are talking about the 1973 Arab oil embargo and then the 1979 Iranian Revolution. Before these events, diesel fuel was cheap. You didn't really have to think about it.
It was just a minor line item on the budget.
Yeah. But then petroleum prices didn't just go up, they nearly quadrupled. By 1980, crude oil was exceeding $35 a barrel. Now, on the surface, someone listening might wonder, what does the price of oil have to do with flattening a field of dirt?
It all comes down to the sheer weight of water.
Okay, break that down for us.
Pumping irrigation water out of a deep underground aquifer is a massive mechanical effort. You are using these vertical turbine pumps to lift millions of gallons of water hundreds of feet straight up against gravity.
Which takes a lot of power.
A massive amount. That requires industrial-scale diesel engines running around the clock. And if your field is natural, meaning it has high spots and low spots, you have to pump a massive excess of water just to ensure the high spots get wet.
Because gravity is just going to drag all that water down into the low spots anyway.
Exactly.
Yeah.
So you end up drowning the crocks and the dips.
Right, and parching the crops on the hills.
And just hemorrhaging water out the edges of the field as runoff.
And every single drop of that wasted water represents diesel fuel burned by the pump.
It's literally burning money.
Mm-hmm.
When oil prices skyrocketed, the traditional, inefficient way of irrigating suddenly became financially ruinous.
But if you could grade that field perfectly...
Yes, shaving off the high spots and filling in the low spots so the water glides across the surface in an even, uniform sheet. If you do that, you could reduce your total water consumption by 15 to 25%.
Wow, 25%.
In the economic reality of the 1970s, saving 20% on your diesel pumping costs was the difference between keeping the farm and going bankrupt.
But the cost of pumping water was only half the nightmare. In some places, the ground itself was literally falling apart. I was looking at the geological records for the San Joaquin Valley in California during this era, and the scale of it is terrifying.
It's almost hard to comprehend.
Decades of heavy groundwater pumping had actually caused the physical collapse of the land surface. The entire valley floor was sinking.
The geological term for this is land subsidence. Underneath the San Joaquin Valley, you have these thick layers of clay, known as aquitards, interspersed with sand and gravel aquifers holding the water.
Okay, so aquifers and aqueducts.
Right. Think of those clay layers like a giant wet sponge buried deep underground. The water inside the sponge is highly pressurized, and it's actually helping to hold up the tremendous weight of the earth above it.
But if you drop thousands of high-capacity wells into that aquifer and pump the water out for 50
The
years,
sponge dries out.
and it gets crushed,
Exactly, it dries out, and the immense weight of the overlying rock and soil crushes it flat. The sources describe this as inelastic compaction.
meaning it doesn't bounce back.
Right. Inelastic means the structure is gone. Even if you pump water back in later, the structure of the clay has been permanently destroyed.
So how much did it sink?
The result was that roughly half of the San Joaquin Valley, an area covering roughly 13,500 square kilometers, subsided by more than 0.3 meters.
A whole foot.
And in some localized areas, the ground sank by nearly 30 feet over a few decades.
30 feet. That is wild. So you have diminishing aquifer capacity, skyrocketing energy costs to pump what little water is left, and the ground itself is shifting beneath your feet.
Which ruins whatever natural drainage your farm previously had.
Exactly. Releveling these fields so farmers could use surface irrigation with absolute mathematical efficiency wasn't just a good idea, it was an operational imperative.
And if California was dealing with collapsing Earth, Arizona was dealing with a full-blown international diplomatic crisis.
Oh man, the Arizona situation.
Yeah, we see this specifically in the Gila River drainage area, primarily the Welton Mohawk Irrigation and Drainage District.
Right.
They were heavily utilizing imported water from the Colorado River for flood irrigation.
But they over-irrigated. The desert soils there are tricky, and they poured so much water onto the fields that the local groundwater levels began to rise dramatically.
A lot of people don't realize that can happen in a desert.
Yeah, the water table came up so high that it started waterlogging the root zones of the crops.
So to save the soil from turning into a swamp, the district had to install massive drainage wells to pump that excess water back out.
But here is the catch.
The underlying issue was that the soils in the Welton Mohawk district are loaded with ancient natural salts.
Right.
When they pumped that drainage water out, it was highly saline. And they discharged that salty water right back into the Colorado River system, which flows directly south into Mexico.
And Mexico, understandably, was furious. The water crossing the border was so salty, it was damaging their own agricultural lands in the Mexicali Valley.
It was a disaster for them.
The historical documents show this escalated to the absolute highest levels of the United States government. In September 1973, the National Security Council, directed by Henry Kissinger, issued a federal mandate to completely eliminate the effects of this saline discharge into Mexico.
The federal government essentially told Arizona they had to fix their water runoff immediately or face severe international consequences.
Wow.
This triggered a massive influx of federal funding and pressure to implement precision land leveling across the district. If the fields were perfectly flat, they wouldn't have to over-irrigate, the water table wouldn't rise, and the salty runoff would stop.
Okay, I do have to ask, though, because it almost sounds too convenient. Did we really invent laser-guided tractors just because diesel got expensive and the National Security Council was mad about salty water?
That's a great question.
Oh,
The crises did not invent the laser.
okay.
The foundational laser technology was already being developed in agricultural laboratories in the late 1960s. Researchers were just looking for better ways to lay drainage pipes.
So the tech was already simmering.
Yes. But without the energy shocks, without the ground physically collapsing in California, and without the federal mandates in Arizona, the laser-guided tractor might have remained a niche luxury novelty for decades.
It wouldn't have scaled.
Exactly. The intense crises of the 1970s acted as an evolutionary forcing function. They took a developing technology and turned it into an immediate survival mechanism.
So the necessity is absolute. The pressure cooker is at maximum pressure. But to appreciate the technological leap that saved these farms, we have to look at what they were doing before the laser, because the analog era of earth moving sounds like an absolute nightmare of manual labor and exhaustion.
Oh, it was grueling,
Yeah.
slow, and incredibly prone to human error.
Paint a picture for us.
Right up until the early 1970s, leveling a field involved a field crew of 2 or 3 people using optical survey instruments. They used what is called a dumpy level.
A dumpy level.
Yeah, which is essentially a small optical telescope mounted on a tripod with a bubble level on it.
Okay, so imagine standing out in the Arizona desert. It's 110 degrees, and you have to lay out a massive rectangular grid across a 40-acre field. They were marking intersections every 50 to 100 feet.
Right. And at every single intersection, a worker with a sledgehammer had to drive a physical wooden stake into the hard-packed dirt.
Every 50 feet.
For a standard 40-acre field, that meant taking 700 and 900 individual elevation readings by hand.
And it wasn't just pounding stakes. A surveyor had to look through the dumpy level at a graded measuring rod held by another worker stand on the stake, read the elevation numbers, and write every single one of those 900 measurements down in a dirt-smudged notebook.
Just incredibly tedious work.
And then they took that notebook back to the truck and had to perform manual mathematics using the four-corner or centroid method.
Yeah, the centroid method.
I was trying to wrap my head around this math when I read the sources. They had to take every grid square, calculate the average elevation of the 4 wooden stakes at the corners, compare that average to the target slope they wanted for the whole field, and then calculate exactly how many cubic yards of dirt needed to be cut from that specific square or added to it.
By hand.
By hand for 900 squares.
And once the math was finally done, they had to go back out to the field and mark the stakes with exactly how deep the tractor driver needed to dig or how much dirt he needed to dump.
So now you have a guy driving a massive roaring tractor, pulling a heavy steel scraper blade, dragging up clouds of choking dust.
Right.
He has to steer the tractor while simultaneously looking out the window at these little wooden stakes as he drives past them, manually pulling hydraulic levers to raise or lower his blade based on the markings.
It's insane. A tolerance of plus or minus 3 centimeters was considered acceptable.
Which seems generous.
It does. But maintaining that across hundreds of acres at the end of a 12-hour shift while staring through a dust cloud is nearly impossible. The human fatigue factor alone guarantees a sloppy field.
Which is exactly the problem that the Agricultural Research Service, the ARS, was trying to solve. Specifically, 2 researchers at Ohio State University in the mid-1960s, agricultural engineer James Foose and engineering technician Norman Fauci.
Fauci, yeah. They were working on high-speed plows designed to lay corrugated plastic drainage pipes underground.
Okay, so pipeline.
Exactly. When you're pulling a plow that fast, a guy pulling levers can't react quickly enough to keep the pipe on grade. They realized they needed an off-machine reference.
Off-machine reference, meaning something outside the tractor.
A perfectly straight line hovering in the air that the machine itself could detect and follow automatically.
Enter the helium neon gas laser.
The HENI laser changed everything. It produces a continuous, highly collimated beam of light.
Collimated. What does that mean in this context?
Collimated means the light waves are parallel, so the beam doesn't spread out and get weaker over long distances like a flashlight does. It stays a tight dot. Crucially, the HENA laser emits light at a specific wavelength, 632.8 nanometers.
Which matters because 632.8 nanometers is a very bright, highly visible red light, and that is incredibly effective at penetrating the dense clouds of dust that tractors kick up.
Yes.
If the light couldn't cut through the dust, the whole system would be useless.
Exactly. But early on, Foose and Fauci just mounted a laser on a tripod at the edge of the field and shot a single stationary beam down the trench line.
Which makes sense for a trench.
That works perfectly if you're driving in a straight line laying a pipe. But if you are trying to flatten a 40-acre field, a single laser line is useless. The tractor has to drive all over the field, in circles, back and forth. You can't just follow one line.
Which brings us to Robert Studebaker and the Laser Plane Corporation in Dayton, Ohio. They looked at that single red beam and had a massive breakthrough.
The pentaprism.
Yes. Instead of pointing the laser horizontally down the field, they mounted the laser pointing vertically, straight up into the sky. And right above the laser, they mounted a spinning pentaprism.
The physics of the pentaprism are brilliant. A pentaprism is a 5-sided block of solid glass. Light enters the bottom, bounces off 2 mirrored interior surfaces at exactly 45-degree angles, and exits the side at a mathematically perfect 90-degree angle to the original beam.
So it bends the light perfectly flat.
The magic of the pentaprism is that even if the prism wobbles slightly as it spins, the light will always exit at exactly 90 degrees.
I picture it like a lighthouse beacon, but instead of warning ships away from rocks, it's a lighthouse for tractors.
That's a great analogy.
A small electric motor spins that pentaprism at several hundred revolutions per minute. That single vertical beam of red light is thrown outward, sweeping a rapid, continuous 360-degree circle. It creates an invisible, perfectly flat plane of red light hovering above the entire field, up to a 1,000-foot radius.
And the transmitter base is mounted on highly precise gimbals. If the farmer wants the field to drain slightly to the south, they just tilt the entire transmitter by exactly 0.2 degrees.
Oh, wow. So the whole plane tilts.
Now, the spinning plane of light is tilted. No matter where the tractor drives north, south, east, west, it has an invisible, perfectly accurate ceiling of light hovering over it, giving it a constant reference point.
So we've solved the math. We have a perfect, invisible ceiling telling us exactly where the ground should be. But, light doesn't move dirt.
No, it certainly doesn't.
It's just photons hitting a piece of glass. How do you take a gentle beam of red light and use it to control a 20-ton piece of machinery violently ripping through hard clay?
That is the core engineering challenge of the system, the transition from optical data to mechanical force. The tractor needs a sensor to read the light.
Right.
But the first massive technical hurdle they ran into had nothing to do with the tractor. It had to do with the sky. How does an electronic light sensor on a tractor tell the difference between a red laser beam and the overwhelming, blinding glare of the actual sun in the middle of a July afternoon in California?
Because the sun emits massive amounts of visible and infrared light. If you just put a simple photocell out there, the sun would instantly blind it. The sensor would think the laser was everywhere all at once.
Exactly. The solution was signal modulation. The engineers mechanically and later electronically chopped the continuous laser beam.
Chopped it.
They pulsed the laser on and off at exactly 150 hertz 150 times a second. Then they designed the silicon receiver on the tractor with a bandpass filter.
So it filters out the static?
The receiver's electronics were tuned to ignore all the steady, continuous light of the sun and only listen for a light signal that was strobing at exactly 150 pulses per second.
It's like being in a crowded, noisy room, but you're only listening for someone tapping a specific Morse code rhythm. Once they beat the sun, they had to design the receiver itself. And this is a beautiful piece of hardware. It's a 30-centimeter tall vertical array of solid-state silicon photocells mounted on a tall metal mast right above the tractor's scraper blade. As the tractor drives, that spinning plane of laser light hits the receiver.
But the receiver didn't just have an on or off switch. The sources describe a highly sophisticated 5-zone logic system.
Why 5 zones?
Because if the sensor only knows the blade is too high or the blade is too low, the machine will jerk violently trying to correct itself.
It's like a teenager learning to drive a manual transmission stick shift. You let the clutch out too fast, the car jerks forward, you panic and slam on the brakes, and suddenly you're just bucking wildly down the street. There is no finesse.
That violent overcorrection is exactly what happened in the early trials. To fix it, they broke that 30-centimeter sensor into 5 distinct zones.
Okay, walk us through the zones.
If the laser beam hit the very top of the sensor, that was the high zone. The system knew the blade was way too high and commanded a fast down response. If the light hit just above the center, that was high-slow, commanding a gradual down movement to ease onto the grade.
Makes sense.
The center was the on-grade null zone, do nothing, the blade is perfect. Then you had low-slow for a gradual up and low for a fast up if the blade was suddenly digging a trench.
So the light hits the specific zone on the sensor. The sensor sends a tiny electrical signal through a wire into a control box sitting in the cab with the driver. And that control box is wired directly into the tractor's hydraulic system. It pulses the hydraulic solenoid valves.
And those solenoid valves are the critical translation point. A solenoid is an electromagnet. When the tiny electrical signal from the laser receiver hits the solenoid, it magnetically pulls open a heavy steel valve.
And that unleashes the fluid.
Exactly. This allows high-pressure hydraulic fluid flowing at over 2,000 pounds to square inch to surge through heavy rubber hoses and push the massive steel hydraulic cylinders that physically lift or lower the 3-ton scraper blade.
But even with the 5-zone logic, getting those hydraulics to behave smoothly was a nightmare. The early systems used what engineers call bang-bang control.
Bang-bang control, right.
The hydraulic valve is either 100% open or 100% closed. There is no in-between.
Which leads right back to that teenager driving the stick shift. When a bang-bang valve fires, the scraper blade drops violently. It goes too low, the sensor reads low, and the valve fires violently the other way, ripping the blade upward.
So it's overcorrecting constantly.
The system starts chasing its own tail. The technical term for this is hunting. The blade oscillates wildly above and below the laser grade line, leaving the field looking like a washboard.
To solve this, those ARS researchers, Fos and Fauzi, actually had to run complex mathematical simulations using early analog computers. They had to mathematically model the nonlinear dynamics of a plow being dragged through dirt.
It was incredibly advanced for the time. They discovered that the hydraulic response speed had to be perfectly tuned to the forward velocity of the tractor.
Right.
If the tractor is moving at 4 miles per hour, the blade can only react so fast before it starts hunting. Their analog simulations proved that tuning the hydraulic hunting cycle frequency to somewhat below 1.0 hertz provided the perfect compromise.
So it dampens the reaction.
Exactly.
Yep.
The blade would make tiny, smooth corrections, keeping the cutting edge within fractions of an inch of the target grade. By the late 1970s, the industry moved from bang-bang valves to proportional control valves, which could open just a tiny sliver for a smooth, graduated response. But it was those early analog computer models that proved a massive tractor could be tamed by a beam of light.
So we have the brains. The pentaprism is spinning, the mast is reading the 150 hertz pulses, the 5-zone logic is calculating the error, and the hydraulic solenoids are seamlessly firing to adjust the blade. But as we said earlier, light doesn't move dirt. We need the muscle.
We definitely need the muscle.
Right. We are talking about ripping up and relocating millions of cubic yards of dense, compacted, rocky soil.
Earth moving at this scale requires immense mechanical brawn. But when we look at the equipment used in agriculture, we have to draw a sharp contrast with heavy civil construction.
Yeah, that's a good point.
If you are building an interstate highway, contractors use motorized, self-propelled scrapers. Think of the massive Caterpillar 621 or 631 machines. These are essentially giant bathtubs with a cutting edge on the bottom, and they have their own massive diesel engines integrated directly into the frame. They load the dirt, haul it, and dump it entirely under their own power.
But the historical records are incredibly clear. Those motorized scrapers are not what the farmers were using. The true heroes of the agricultural land leveling revolution were tractor-towed pull-type scrapers.
Yeah, pull-type scrapers.
And the reason comes down to capital costs and farm economics.
Absolutely. A motorized scraper is a highly specialized, incredibly expensive single-purpose machine. It only does one thing: move dirt. A farmer, or even a local agricultural contractor, cannot justify tying up hundreds of thousands of dollars in an engine that only works during the short grading season.
It just sits there the rest of the year.
Exactly. But they already own heavy tractors, so why not just buy the scraper bowl, which is essentially a heavy steel box on wheels, hitch it to the drawbar of the tractor you already have, and plug the hydraulic hoses into the tractor's existing system.
It was an incredibly versatile and economical solution, and this era gave rise to some legendary manufacturing titans who specialized in these pull-type scrapers.
Reynolds is the big one.
Yeah, Reynolds Scrapers out of McAllen, Texas. They emerged as the undisputed industry leader. They built the LSE series, which literally stood for Laser Scraper Ejector. These things were monsters. A single LSE scraper could hold up to 17 cubic yards of earth.
They wouldn't just pull one.
Right. Contractors would set them up in tandem, hitching two massive scrapers behind one tractor to move nearly 40 cubic yards of dirt in a single pass.
Then you had regional specialists. Up in Idaho, you had Miskin Scraper Works. They had been making horse-drawn scrapers since 1917. In the 1970s, their hydraulic pull-type scrapers dominated the Intermountain West because they designed their equipment specifically to handle the incredibly brutal, volcanic, rocky soils of that region.
Specialized for the rocks.
Yep. And down in Georgia, the Rome Plow Company leveraged their legacy of building heavy land-clearing equipment for the military to build heavily armored scraper bowls that wouldn't buckle under extreme stress.
But dragging 17 to 40 cubic yards of dense, heavy dirt is no joke. You cannot do this with a lightweight machine. The sheer draft power required to pull that steel blade through hard clay birthed the golden era of the heavy, four-wheel drive articulated tractor.
To pull these scrapers effectively day after day, contractors turned to massive industrial machines. Brands like Steiger, operating out of Fargo, North Dakota, and Versatile, building machines up in Canada.
Why Steiger and Versatile? A lot of farmers had regular row crop tractors. Why did they need these massive 4WD articulated beasts?
It comes down to torque and bending loads. Pulling a heavy scraper puts extreme variable stress on a tractor's frame and axles. When the blade bites into a hard ridge of dry clay, the shock load sent through the drawbar is violent.
Oh, I bet.
A standard farm tractor would literally tear itself apart over time. Steiger and Versatile dominated the professional earth-moving market because they didn't just scale up farm tractors. They built their machines using robust, heavy-duty commercial truck and industrial components.
So they were built like tanks.
Pretty much. They utilized massive planetary final drives and reinforced steel axle tubes designed for the logging and mining industries. The frames pivoted in the middle to steer, meaning all four massive tires were constantly clawing for traction.
Though it is important to note that traditional two-wheel drive row crop tractors still had a vital role to play in this ecosystem. We are talking about machines like the wildly popular John Deere 4430. That specific tractor was a massive game changer, not because of its pulling power, but because of its cab. Specifically, the Generation II Soundguard cab.
The introduction of the SoundGuard cab completely transformed the human element of agricultural labor. Before this, operators were sitting entirely exposed to the elements, breathing in choking dust, deafened by engine roar, baking in the sun.
Such miserable conditions.
The SoundGuard was an enclosed capsule isolated from the tractor frame by thick rubber bushings to dampen vibration. It had thick foam insulation, integrated air conditioning, and a massive curved windshield for visibility.
Wow.
For a land-leveling operator pulling a 12-hour shift dragging a scraper, that cab transformed the job from a brutal, exhausting physical endurance test into a comfortable, modern profession.
And those row crop tractors were essential because the actual act of leveling a field does a lot of hidden damage. When you drive a 15-ton Steiger, pulling a 10-ton scraper full of dirt back and forth across a field 100 times, you severely compact the soil.
Yeah, soil compaction is a huge issue.
You crush the pore spaces in the dirt that roots need to breathe. So after the laser scrapers achieved the perfect mathematical grade, farmers needed those nimble row crop tractors to come in and pull deep tillage rippers.
Right, to break up that hard pan.
Exactly. Massive steel shanks that dig 3 feet deep to shatter that subsoil and alleviate the compaction without ruining the surface grade.
It was a whole sequence of heavy machinery operations. And I know some people might wonder why John Deere, the biggest name in agriculture, didn't dominate the massive articulated 4WD scraper market with their 8430 and 8630 models.
They definitely tried. They built massive 4WD machines.
They did, and they were incredibly powerful tractors. But the historical engineering records show that the 8630 in particular struggled with hydraulic reliability issues when subjected to the intense, continuous, high-flow demands of laser scraper work.
Interesting.
The hydraulic oil would overheat under the constant cycling of the proportional valves. Contractors found themselves returning to Steiger and Versatile for the primary earth-moving simply because their simpler, truck-based hydraulic systems could handle the brutal, continuous duty cycles.
Which brings up a really practical question. If you were a farmer in Arizona in 1975 staring at a federal mandate to fix your salty runoff, and you need to laser level your farm to survive.
How do you actually do it?
Right, how do you actually get this stuff?
Yeah.
You can't just flip through a Sears mail order catalog and order a 300 horsepower Steiger and a laser plane Pentaprism. It requires a massive amount of capital, technical training, and part support.
That is where the commercial ecosystem comes into play. The hardware is useless without the distribution networks to finance it, train the operators, and fix it when hydraulic hose blows at 3 a.m. The 1970s saw the rise of the specialized mega dealers.
Let's talk about the Quinn Company. They were headquartered in Fresno, right in the geographic heart of the San Joaquin Valley. As we established, the valley floor was literally sinking due to the subsidence crisis.
Yes.
Quinn recognized the existential threat to the region's agriculture and acted as a massive technological hub. They set up dedicated laser leveling divisions, specifically to supply heavy Caterpillar machinery and laser technology to the massive farming conglomerates fighting to save their water infrastructure.
And over in Arizona, fighting the Welton Mohawk salinity crisis, you had Empire Southwest. They were the exclusive Caterpillar dealer for the region, and they were highly aggressive in supplying the heavy dozers required for initial civil earth moving and the precision scrapers needed for the final basin leveling.
Wow, so the dealers were heavily involved.
Very much so. You also had the O.S. Stapley Company, an absolute titan of agricultural distribution. They were the oldest international harvester dealer in the West, with massive service locations all across Arizona, supplying the tractors required for the region's agricultural expansion.
These dealerships were essentially the quartermasters on the front lines of the water wars. They provided the financing, the mechanic fleets, and the training. But the tractors and scrapers were only half the equation. They also had to sell the lasers. And Laserplane, the company in Ohio that invented the rotating Pentaprism, was not alone in the market for long.
Not at all.
A fierce, highly competitive laser ecosystem emerged almost overnight.
A lot of highly technical startups jumped into the fray. You had companies like Blount and George in Arkansas, which eventually evolved into the AGL Corporation. AGL played a massive role because they solved a major practical problem.
What was the problem?
Early laser transmitters required a massive amount of electricity. Farmers were literally dragging heavy automotive car batteries out into the mud to power the lasers.
Oh, that sounds awful.
AGL was the first major customer for a startup that developed a compact, switch-mode power supply for helium neon lasers. This shrank the power requirements, allowing the technology to be packaged into a much more manageable, portable footprint.
You also had Laser Alignment Inc. up in Michigan. They were aggressively patenting new light target arrays and sensor designs, trying to beat laser planes' five-zone logic. And you had Topcon, a massive Japanese optical engineering company.
Topcon is still huge today.
Yeah, they established their American subsidiary in 1970 and started laying the groundwork, aggressively acquiring optical technology, building what would eventually become a massive precision agriculture portfolio.
The money pouring into this sector was staggering because the technology was so revolutionary. But this fierce competition led to a critical, almost inevitable moment of corporate consolidation.
Consolidation.
Yes, in December 1976, Spectra Physics, which was a massive, highly successful California-based laser company, acquired the Laserplane Corporation. This brought the foundational patents of the rotating pentaprism and immense corporate manufacturing power under one roof.
And the federal government definitely noticed. This wasn't just a niche farm tool anymore. It was rapidly becoming critical national infrastructure. According to the historical legal filings, specifically Civil Action, no, C-70 1879 TEH, the United States Department of Justice actually filed a civil antitrust complaint against Spectra Physics in 1978.
The DOJ's primary concern, as outlined in their filing, was that this acquisition substantially lessened competition in the newly emerging machine control laser market.
They were worried about a monopoly.
Exactly. They feel that a single entity was gaining a monopoly over a technology that was absolutely critical for the survival of American agriculture and heavy construction. A consent judgment was eventually negotiated, forcing certain patent licensing agreements, and the combined entity went on to be the dominant force in agricultural lasers for the rest of the century. But the fact that the DOJ stepped in highlights just how vital that invisible beam of light had become to the American economy.
So we have the crises acting as the forcing function. We have the helium-neon laser tech. We have the complex hydraulic feedback loops and analog computers. We have the heavy iron muscle of Steigers and Reynolds scrapers, and the mega dealers supplying them. What did this actually look like when it was fully deployed in the field?
That's where it gets really interesting.
What blows my mind is that you have guys in the bone-dry Arizona desert and guys in the flooded swamps of Arkansas buying the exact same multi-million-dollar laser systems, but using them to do the exact opposite things with water.
The regional agronomic outcomes are fascinating because the technology is completely mathematically agnostic. The laser just shoots a flat plane. It is up to the local engineers to decide what angle that plane should be.
Right.
But before we look at the crops, we have to look at one of those unexpected and highly profitable byproducts of transitioning from optical surveying to laser control. The laser unlocked at the night.
Owning the night. I love this detail so much.
Think about the physics of the old manual method. With an optical dumpy level, the human surveyor has to be able to physically see the painted numbers on a wooden grade rod through a telescope. You can only work when the sun is up.
Yeah, that makes sense.
The moment the sun sets, Earth's moving stops. But the laser system relies on a projected beam of light hitting electronic photocells. The silicon receiver doesn't need ambient daylight to see the laser strike. Therefore, leveling contractors realized they could run their Steiger tractors and Reynolds scrapers 24 hours a day.
And what's wild is that they actually preferred working at night because during the day, especially in places like the Central Valley of California or the deserts of Arizona, the sun violently heats up the bare soil. This creates what engineers call heat shimmer.
Ah, the heat shimmer.
It's that wavy, watery mirage effect you see hovering over a hot asphalt highway. Those are refractive index variations in the superheated air, and those variations would actually bend and distort the red laser beam as it traveled across the field, causing the tractor sensors to receive false elevation readings.
The heat shimmer ruined the mathematical precision. But at night, the desert air cools down, the thermal layers stabilize, the shimmer disappears entirely, and the laser cuts a perfectly straight, crisp plane through the dark.
So it's actually more accurate at night.
Completely. It completely changed the economics for the leveling contractors. They could double their operational hours during the very narrow seasonal windows between the fall harvest and the spring planting. Imagine the visual of these massive, 300 horsepower articulated tractors roaring across the desert at 2 in the morning, bathed in floodlights, guided silently by an invisible web of red light hovering in the darkness.
It's an incredible visual, but what were they actually building in the dark? Let's go back to Arizona and the Welton-Mohawk salinity crisis. They used these night ops to perform something called dead leveling.
In Arizona, the primary objective was to combat the highly saline runoff polluting the Colorado River and to stretch their imported water allocations to the absolute maximum. To do this, their engineers designed perfectly flat agricultural basins with absolutely zero slope. dead level.
Literally flat, like a table.
Exactly. They would use the Steigers to throw up small dirt berms around a 40-acre square, and then use the laser scrapers to plane the interior until it was mathematically flat.
So when the farmer opened the irrigation gates, the water didn't run down a hill. It flooded the entire basin rapidly and uniformly. It soaked straight down into the root zone of the crops like a giant bathtub, filling up perfectly evenly. There was no low spot for the water to pool in, and there was no excess water running off the end of the field carrying salt into the drainage ditches.
It was a massive success for water conservation in arid environments.
Right.
But then you travel thousands of miles away to the American South, to the heavy, sticky clay soils of Arkansas and the Mississippi Delta, a region that receives massive amounts of rainfall.
Right.
And yet they also adopted the exact same dry climate laser technology.
But they used it to completely revolutionize how rice was grown. I was reading about an Arkansas farmer named Leroy Isbell, who is widely credited with pioneering something called zero-grade rice farming. Traditionally, if you look at an old rice paddy, it's terraced.
Terraced, right.
Farmers would build these curved, meandering contour levees out of dirt that followed the natural, uneven curves of the land to hold the floodwaters in. The field looked like a topographical map.
Isbell realized that if he used the laser-guided scrapers to plane those heavy clay buckshot soils until they were perfectly flat, just like the dead-level basins in Arizona, he could eliminate the traditional contour levees entirely. He turned the entire field into one massive, flat paddy.
The results were staggering. By eliminating the levees, he reclaimed acres of plantable land that used to be covered by dirt walls. The water flooded uniformly across the whole field with minimal effort. The USDA sources show this zero-grade laser leveling saved up to 60% on water usage compared to traditional contour levees.
60%.
They saved an absolute fortune on the diesel required to run their groundwater pumps.
But if you travel just one state south, into the sugarcane fields of Louisiana, doing a zero-grade dead-level field would be an absolute agronomic disaster.
Because sugarcane roots will suffocate and die if they sit in standing water.
Precisely. Louisiana receives torrential heavy rainfall. The goal there isn't to hold the water in a basin. The goal is to get the water off the field as fast as physically possible before the sugarcane drowns.
So they want it to drain.
Yes. So they bought the exact same Reynolds scrapers, the exact same laser plane transmitters, but instead of setting the gimbals to 0, they carefully tilted the laser transmitter to create highly precise calculated slopes, usually about a 0.1% or 0.2% grade.
Just the tiny tilt.
Just enough. This allowed the heavy tropical rainfall to rapidly and safely sheet off the fields into lateral quarter drain ditches, maximizing their sucrose yields. It is the exact same hardware, just dialed to a different mathematical solution based on the hydrology.
And arriving at those mathematical solutions was the final piece of the puzzle that experienced a quiet revolution in the 1970s. We've spent a lot of time talking about the hardware, the tractors, the hydraulics, the heavy iron. But we have to talk about the math.
The math is crucial.
Because even if you have a laser that can guide a tractor, a human engineer still has to calculate the plane of best fit for that field. They have to figure out the exact slope that minimizes the total amount of dirt you have to move, because moving dirt costs diesel while still achieving the desired drainage. Before the mid-1970s, calculating that plane of best fit using the least squares method took hours of grueling manual arithmetic.
The design process was the massive bottleneck. The tractors could move dirt faster than the engineers could calculate the cut sheets, but then came the handheld programmable calculators. Specifically, machines like the Hewlett-Packard HP65 introduced in 1974 and the Texas Instruments TI-59 in 1977.
These weren't just calculators, they were pocket-sized computers. Suddenly, engineers and soil conservation service technicians could store complex cut-and-fill mathematical programs on these tiny little magnetic script cards.
They could stand out on the tailgate of a pickup truck, punch in the raw grid elevation data they took from the field, run the magnetic card through the calculator, and the machine would output the perfect mathematical field design, calculating the exact cut and fill volumes for the scrapers in a matter of minutes instead of hours. The engineering design process finally caught up to the mechanical execution speed.
It is just an incredible, sweeping journey. When you step back and look at the whole picture, we started the 1970s with guys standing in the blistering sun, staring through optical tubes, violently pounding woody stakes into the earth, and guessing at levers while the ground in California literally collapsed beneath their feet, and international diplomats threatened them over salty water.
It was a very precarious situation.
And within a single decade, forced by those compounding pressures, we witness the synthesis of incredible technologies. The helium neon laser cutting through the dust, the rotating pentaprism creating an invisible ceiling, the 150 hertz modulated sensors beating the sun, the analog modeled hydraulic feedback loops taming the bounce, and the sheer brute force muscle of 300 horsepower Steiger tractors dragging 17-yard Reynolds scrapers.
Together, they didn't just improve farming. They literally reshaped the surface of the American continent. They achieved a topographical transition that saved countless millions of gallons of diesel fuel and conserved massive underground aquifers in the process. We stopped adapting our machines to the natural, uneven shape of the Earth and started violently forcing the Earth to conform to our perfect mathematics.
It was the dawn of precision agriculture, the moment we replaced human estimation with absolute automated certainty. So what does this all mean for you? Every time you drive down an interstate highway and look out the window at a perfectly uniform crop sitting on a perfectly flat field reaching to the horizon, I want you to remember that you are not looking at raw nature. You are seeing the physical, permanent result of an invisible architecture of light.
That's a powerful way to look at it.
But exploring this history leaves me with a somewhat provocative thought to ponder. Today, if you go to a modern farm, the rotating lasers are slowly disappearing. They are being replaced by massive arrays of orbital GPS satellites and highly automated digital screens inside the tractor cab. The machines are driving themselves based on invisible coordinates floating in space.
It's true, GPS is taking over.
As we move into an era completely reliant on digital satellite signals, what happens if those complex digital systems fail? Do we still possess the analog skills, the raw, visceral ability to read the natural contours of the land with our own eyes? Or have we permanently outsourced our fundamental understanding of the Earth to the very machines we built to conquer it?
That is a profound question to consider the next time you look out over an open field.
Thanks for taking this deep dive with us.